do we need the nuclear models and how many varieties of nuclear models are there. So these two questions we will try to answer in today's lecture. Now, well, I have already discussed about the deuteron problem, right, and the scattering issues as well. So let's start with that. So first we will talk about the need for nuclear models, right. So need for nuclear models. Now, well, we have already studied the nuclear two-body problem, okay, and the internucleon forces. What have we found about them? Basically, from our study of two-body problem, we have observed that the nuclear force, regarding them, there is no derivation. So for nuclear force, we have observed that there is no derivation for them from first principles. Right, this we have observed. Now, for this study, however, we have been able to obtain considerable information about the nuclear force. So basically, even though we have found that there is no derivation possible for it from the first principles, still from these two body forces we have obtained great deal of information. You can check my lecture as well online, and I have already covered this in class. Now, as it turns out, basically this force is very complicated. This we have found, and very different type of behavior compared to your normal forces. Very different behavior. Now, when I am saying very different behavior, I am saying from a numerical point of view. Forget analytical form, it does not exist. In a way, it changes depending on the several factors are there. Again, you cannot even talk about it numerically, it is very hard. So numerical point of view, okay, and also this shows a very strong repulsion or hardcore at short distances between the nucleons. Now, so this we know about the nuclear force, and right now we have talked about the nuclear two-body problem. But the nucleus doesn't just consist of only two nucleons, right? The mass number can vary, right? And basically we can have capital A ranging around, sometimes it can be even 300 or so. So let me talk about real nuclei. What happened to them? So this was the information basically from the two-body problem. Now from say, for the real nuclei, there are even more issues compared to your two-body problem. This is just the beginning of our tough life for studying nucleus. Now you see, the nucleons in both your two nucleon system like deuteron and your normal nuclei, they actually do not feel the bare nucleon force. This is very important, and there seems to be presence of many body forces. This is one very issue. Even though we can find some bare form of nucleon force inside the nucleus, this doesn't work. This will change inside the nucleus. And also there are presence of many body forces. Now I am not going to talk about the evidence, but let me right now talk about the important issues which are at hand. Now, so what are we going to study right now? Basically our aim is the study of nuclear structure, right? And basically we will be using our nuclear models for this study. So we will use nuclear models to study nuclear structure. Now the first thing is, what is nuclear structure? Right? Basically, nuclear structure, this includes all information about properties of nuclei. Now when I say all new information, I mean regarding the properties, how nuclei are bound inside nucleus, okay. Next, what are their paths, how are they moving inside nucleus, okay. Next, what are their linear and angular momenta, fine. Next, is there any correlation, does it exist, any relation, any correlation between them, and various other properties like spin, parity, electric and magnetic moments. Next, charge radius, okay, and all that. Now basically this is what nuclear structure is all about. Well, you see, the theoretical determination of all these properties is the right way to do, and then we will try to match them with the experiment. This is how we do in physics. So now regarding the theoretical determination of these properties, this will require the calculation of the total wave function of the nucleus. Total wave function, that means the nucleus total wave function. Now remember, this wave function I am talking about all the nucleons inside the nucleus, their total wave function. Now you see, for our nuclear system, this I have already talked about previously. Say for A greater than 2, we have to face several difficulties. Now, what are those difficulties? See, the first difficulty is that we do not have a clear idea of nature of the nuclear force or nuclear interaction. The second difficulty is, so this is number 1, then number 2 is, even if we assume forces of simple forms, this we will do, this is how we proceed, simple form which contain important aspects of the nuclear forces characters, such as short range, then spin dependence, tensor component, etc. Then you see there is at present no simple approximation procedure using which we can reasonably calculate the accurate solutions of the many body Schrödinger equation. You understand? These are the two great issues at hand, and as a result we look for, so that's why what we do is, because of these two very important issues, we look for mathematical models based on certain very simplifying assumptions, which without too heavy calculations, come on, these are already involving so many calculations, we don't want to do that because they are very difficult to perform. So we want to use a path of lesser calculations, more simplicity. So this is the path, and this is the path towards the nuclear model. So basically, again I am repeating, we are looking for, as a result, mathematical models based on certain simplifying assumptions which without too involved calculations can give us or provide us satisfactory description. Remember, I am saying satisfactory because I don't expect to get all the answers, because I am not doing the correct thing. This was, the tackling of this issue was the correct thing. This is not possible to do. So I am going to a shortcut, which is lesser calculation, simpler way. And so, since you are doing a shortcut, you don't expect the perfect behavior to be, you don't expect your methods to give you everything that experiment gives you. So basically, when you will use these techniques, you already expect that, come on, there will be some deviations of my expectations from the experiment, because we have not done the correct thing, because it is not possible at this moment to do the correct procedure. And so my involved calculations using these mathematical models will just give me satisfactory description of various characteristics of nuclear structure and the various nuclear properties. So this is the reason why we use nuclear models. And these mathematical models, which I told you just now, these are basically conceptual models. These are our nuclear models. Okay. So any question? I have basically talked about the basic idea of why we need nuclear models. Remember, nuclear model is basically an escape route. This is basically an escape route because of the complicated nuclear force and the many-body Schrödinger equation solving with many-body complex nuclear force, which is not just two-body effect. So basically we are talking about an escape route, an alternative route to understand the structure of the nucleus. So this is the nuclear model way. Okay. Now regarding this total wave function, I must say that it is in fact possible to find the total wave function for the simplest of the nuclei, say two-body nuclei where only two nucleons or maybe three nucleons are present. That is few body problem. But what about the heavier nuclei? Well, you see, say for a nuclei having 150 nucleons. What about it? Now in that case, for such a complex nucleus, medium mass nucleus, the total wave function, suppose it's available to us. The thing is that even if it is available, it becomes available, it will be too complicated to be of any practical use. So what is the way out? Since even if the solution is there but we cannot use it practically, then this is as equivalent to having no solution at all. You understand? So the summary is that in absence of the exact theory, or even if the theory is present but we are unable to use this practically, no, in such situations we have the solution of our nuclear model. Now again, let me emphasize that the nuclear models that were developed, they were developed under several simplifying assumptions. Of course, that was the basic idea. Now, so we have got several nuclear models, but remember each nuclear model consists of certain simplifying assumptions which is different from each other, and as a result each model is capable of explaining only a part of our experimental knowledge about nuclei. So if this is the entire experimental knowledge, then each of the models, each one, say 1, 2, 3, 4, 5 models, they will explain only a part. Sometimes there will be an overlap, but mostly they will be able to explain each of the part, because you see the underlying assumptions are different. Okay. Now before I finish, let me talk about also this important thing. You see, I talked about the fact that it must give us satisfactory results for the various nuclear structure and properties. So what nuclear properties am I going to talk about? Okay. Now basically the various nuclear properties, they can be, you see, the spin, again ground state, okay, magnetic moments, electric quadrupole moments. So these are the various properties. Again existence of isomers. Next, parity of the level, right? Then we have got how we have to explain the consistency of binding energy per nucleon. Next, we have to explain the fission, again non-existence of nuclei which are heavier than 238 uranium or so. Next, let us talk about individual nucleons. Then we have to talk about the wide spacing of low-lying excited levels in nuclei, whereas the higher lying levels have quite close spacing. Okay. Then again, existence of resonance capture reactions, and you see there are many more features. So for each one of them you can say we have got a separate model at hand, and this we will now study. So the next talk I will talk about basically the evolution of nuclear models. Some history will be there, but you will be able to know about the basic features, the underlying physical principles of the most important models that we use today.